Kazakhstan, and Team Czechia will be opposing Team Hungary. And you can challenge on the problems that is written down on the blackboards. I have removed 12 because it was reported in stage 1. So those 8 problems can be challenged upon.
So we would like to challenge you to the task number 10, the renewable winner convection.
Task number 10 challenge.
We accept the challenge.
Problem number 10 accepted. Yes, you can start.
So, welcome everyone. My name is Milan Steinay, and this is my solution to problem number 10, Rayleigh-Bénard convection. The problem states that if we uniformly and gently heat a container at its bottom, and we have a suspension of powder in some oil inside the container, cell-like structures, like which can be seen in the picture 4, and my job was to explain and investigate this phenomenon. So let's start with some basic physics. The key mechanism looks like this. First, we add the temperature difference to the container, and it creates a density difference, which results in a buoyancy difference. So fluid rises and then descends if some critical conditions are met. This is our system where you can see the temperature from the bottom, and this is one cell, or like one half of a cell. The main parameters for our system is the temperature difference, the fluid properties, and the geometrics of the container. So, some theory for the instability. This is our system once again with the temperature gradient. It has a fluid depth of L, and the convection will develop if an initial small perturbation will grow in the system. So, if a small volume of water spontaneously rises by delta Z, then we can first assume a linear temperature profile just before the start of the convection. So the temperature difference of the small packet of volume to its environment will be small delta Z. And then we can write down the thermal diffusion equation. And we can approximate the Laplacian of the temperature like that. From this, we can calculate, or we can define a thermal diffusion timescale, which is the time it takes for that small packet of water, or no, sorry, fluid, to cool down to its environment. We can also assume balance of forces, and we can look at the motion of the small packet downwards with a constant velocity, and then we can write down the buoyant force like this. It results from the density gradient, the density difference, and we can, based on Newton's law, we can write down the viscous force like this, where we approximate the gradient of the velocity like that. And if we equate these two equations, we can calculate the velocity of the small packet of fluid. And from this, we can define displacement time, which is the time it takes for the fluid to go back to the bottom of the container. And we have the very important number in the system, the Rayleigh number. This is the ratio of these two time scales. These are the relevant parameters of the system. They are mostly contained in this Rayleigh number. And so the ones on top support the convection, while the ones on the bottom inhibit the convection. For this configuration, during my measurements, the critical Rayleigh number is around 1,700. And in my experiments, I've used that range of Rayleigh numbers. So let's look at my measurement methods. The general setup looks something like this. We have a glass ball, which is see-through. Then we have the particle suspension in silicon oil. I have used silicon oil. I have used water heating to ensure gentle and uniform heating. And I also used two temperature sensors, which were point-like, and they were calibrated beforehand. I have two distinct setups. The first one is when I use mica powder, as the problem statement suggested. That is for top view analysis, while the second one is a PIV setup for cross-sectional analysis. But what is PIV? Well, here we have our system, and to do PIV, we first take a laser, and we shine through the whole container. And then the laser plane will cut through the container, and we will see a 2D section. And we can look at this 2D section and analyze the structure of the flow. For that, we use PIV particles, which are fluorescent, so that's why they kind of reflect and they are visible on the inside the 2D plane. And I have taken 30 FPS videos of the particles in motion to analyze, and I have analyzed consecutive frames. From that, I was able to derive some velocities and internal structure in my system. Once again about the particle initial symmetry, the results look something like this. We have, this is a video, and here we can see the streamlines, so the structure of the convection. But we also get a velocity field where the color is the magnitude of the velocity, not the direction. That is very important. So, about the critical Rayleigh number. This is a video of a low Rayleigh number experiment. And here we can track the Rayleigh number over time, as well as the number of cells over time. And what we can observe is that when the Rayleigh number the cells start appearing. So this measurement proves that the critical real number is in the 7300. And there you can see that for low real numbers, this is a very stable system, and the cell structure remains very stable. Now, this is a high real number experiment, and here we once again track the real number and the number of cells over time, and here we can observe a peak, and after that, a stabilization, because the whole motion of the cells are quite well, I'm going to say turbulent, but they move against each other, and then they need some time to stabilize. However, the key parameter here, so why does the real number increase? Because of the temperature difference, which we add during my setup, during my measurements. So we now look at the influence of the temperature difference in my system. This is the velocity field from the PIV results, and here we can analyze this the following way. We first look at a row and we average the velocities, the vertical velocity components in that row, and then we do this throughout the whole video, and we get a graph like this, where for every exposition we get an average velocity of the fluid. Here what we can observe is that there are some peaks and valleys, and the peaks correspond to the upward motion of the fluid, while the valleys correspond to the downward motion of the fluid. So inside the cell in the center, the fluid rises, and outside it descends, so we can analyze the cell structure from these kind of graphs. And we can also average the velocities in the horizontal direction. Here we only average the magnitude of the velocities. We once again do it all over the whole vertical pixels, and we get a video like this, where we can observe that the maximum velocity is up there at the top of the cell. That's where the fluid rises and then quickly spreads at the top of the cells. So if we have a larger temperature difference in our system, then we have more potential in it. So the rise velocity will be higher. So, and once again, for a small volume of fluid, since the buoyant force is proportional to the temperature difference, while the viscous force is proportional to its velocity, we can then, if we once again use our previous model, the balance of these two forces, we will get a result that the average velocity of rising will be proportional to the temperature difference, and I have these measurements for that, and you can clearly observe this linear trend. It is very important. However, we also have a change in the structure over time, and for that I've used a different setup. I once again took a laser and shined it through the container. However, now I tracked the laser point on the screen, and this laser point slowly moves around. So I have analyzed this digital tracker, and then I have looked at these graphs. And there are a couple of things you can observe. First, for smaller real numbers, the frequency of this oscillation is quite low. However, for higher real numbers, we can actually observe two different frequencies, a lower and a higher frequency. So why is that? Well, because if cells move very slowly, this will result in a global small frequency oscillation, but there are also changes inside each cell, and these will result in very higher frequency oscillations. So for very low real numbers, we see no detectable oscillations, while for moderate real numbers, there is a small f component, and for very high real numbers, we both have a small and a larger f frequency component. So once again, if we have more potential in the system, the velocities will be higher, so these frequencies will also be higher. And from measurements, we can observe that both the high and both the low frequencies depend on the temperature difference linearly. Now about the cell's size and cell shape, because these are also very important. I have measurements here, the number of cells with regards to the real number, and we can observe a couple of things. The first measurement was conducted with those parameters, and here you can observe the cells from the top, and we see quite symmetrical, quite small cells. However, if we increase the temperature, of course the real number will be increased, and the cells grow in size. For that point, we now well, once again decrease the temperature but increase the fluid depth. So the Rayleigh number once again increases. And now we observe that the cells are much bigger and they are kind of less symmetric, less hexagonal. And for very high Rayleigh numbers, the whole cell shapes are very different and they are not symmetric at all. So why is that? Well, because if you have lower potential in the system, once again the velocity of the rise will be lower, and so the cell size will decrease, because when the fluid rises to the top, it will flow outwards with a lower velocity. However, we also have to take into consideration the container size. It's very important because at the walls, some force is acting upon by the walls onto the whole system. So that's why these walls are a limit in my measurements, and they also affect the cell's shape. But sometimes for higher Rayleigh numbers, the walls are the ones which contain the shapes, the cells, and that's why their shapes won't be that chaotic. And to kind of quantify this, we also looked at the aspect ratio of the container, and for the lower aspect ratios, we see larger cells, whereas for higher aspect ratios, we see smaller and more symmetrical cells. So to summarize everything, I first looked at the Rayleigh number and kind of set up a theory for that. That is the main part of the problem. Then I've also measured with two different configurations. I've did some PIV to analyze the structure as well. I've proved that the onset of the convection starts at approximately the critical Rayleigh number. Then I also looked at the potential of the system, as well as I looked at the change of the structure of the system over time. Thank you very much.
Thank you. Clarifying questions, please.
Yeah. So I would like to ask, what are the conditions for the critical Rayleigh number that you use?
What are the conditions?
Yeah, some assumptions, because critical Rayleigh number would change, for example, according to some boundary conditions. So what are those
boundary conditions were like if we don't have an infinite two plates, but we have some walls, then I say that the critical Rayleigh number is
yeah, because this Rayleigh number is, for example, for no friction walls. So you assume no friction as well.
Yeah, of course.
Yeah.
We have a
Okay. Yeah, and I would like to ask, how did you calculate the velocity field?
Well, from the PIV. So I once again can show you these.
Okay, we will discuss it.
From these.
Yeah. Okay.
Using MATLAB actually.
Yeah. And is the indicator used for the convection needed for the convection to occur? Or would it work without the suspension?
No, it would work with suspension for all.
Yeah. Okay. And how did you measure the parameters of your OEO?
Well, I had a spreadsheet from the producer.
Yeah. Okay. Thanks. Yeah. And could you somehow explain, from a physical point of view, why do we see the cells on the surface?
Yeah. So if I assume you think of like these. If we use nitro powder, we see the cells from the top, and we see them because there are different concentrations of nitro powder at different places, and its optics work. So basically, the fluid is rheoscopic, and it shows the streams and velocities.
Yeah. Okay.
So the cells.
Yeah. Okay. And in the beginning, you talked about the linear gradient of the temperature.
Yeah.
So is it needed, or is just for the visualization?
Well, just before the convection occurs, it is linear, and it is needed for like setting up this Rayleigh number, which is the most important.
Yeah. So it would it work if you had perfectly you had the oil at a constant temperature?
Yes or
No,
Yes
it
or no?
wouldn't.
Thank you. Preparation time. 30 seconds. You should start soon. Please start talking.
Yeah.
Yes.
So, I am from Team Chica, and I will propose the task number 10, relevant correction. So, to summarize what the reporter said and explained. He explained how the convection begins and how the cells are formed. He derived the Rayleigh number and the important parameters for this phenomenon. He for his experiment he used very nice aperture. He used silicon oil, which we found kind of lacking that he did not use any other oil, but yeah, that's how it is. He used particle image velocimetry, which is kind of cool that he looked on the convection not only from the surface but only from the sides. He talked about the critical conditions for the cell observations, and he also measured them. He talked about the stabilization of the number of the cells, how after some time the number of cells will stabilize and the convection will be stable. He analyzed the velocity field in the convection, and he talked about the dependence on the temperature difference in his experiments. He also described how the frequency of the movement depends on the Rayleigh number, and he analyzed different sizes of the cells. Now to some specifics. We found really great that he looked on the convection not only from the top side, as was stated in the task definition, but he also used the method, PIV method, and he looked on the cross-section analysis, which we found very great, and that he also calculated the velocity field from it. He also analyzed the critical Rayleigh number, and he verified that the critical Rayleigh number for the experiment was around 1700, and he analyzed all the fields from the side to prove that the convection really happens and is there. One of the things that I think was kind of lacking was that he used some assumptions but didn't explain them properly. But after I asked, he described it and answered my question. One thing that I think would be quite interesting would be when he was looking on it from the side, how it was, for example, dependent on the 3D model of the whole phenomenon. So how the 3D of the phenomenon could somehow interfere with the 2D projection. Some of the graphs that he said that were linear, we don't think there are a lot of very big error bars, so we think that's something that we could discuss. And he did not do that much of the measurements, so that's something that I think that's kind of lacking. So now I would like to move to discussion topics, and I would like to discuss a lot of the different parameters that could be changed and how do they change the convection and the size of the cells. And I would like to discuss what else could we get, for example, from the laser measurements, and how was exactly the velocity field measured. I will also like to talk about the boundaries of the fluid of the containers that we use, because I think using two free slip conditions is kind of not relevant for this phenomenon. So I would like to invite the opponent for.
Can I just briefly clarify something?
Yeah.
So you have mentioned that I didn't use multiple silicon oils, but I have done that. Just the Rayleigh number is calculated using all kind of fluid parameters. I have actually used 3 kinds of silicon oils with viscosities, with a dynamic viscosity of 100, 300, and 500 centistoves, or 350, yeah, sorry.
Okay.
So yes.
Yeah. And when we are talking about different oils, what would happen if you set the same Rayleigh number for different oils?
So you mean that I like set out the experiment?
Yeah.
So the Rayleigh number is exactly the same.
Yeah. what would happen?
And what parameter are you interested in?
Yeah, I think for the first one that comes to my mind is the size of the cells.
Yes. Well,
How would it be changed? Or would it be?
I would say that the size of the cells mainly depend on the temperature gradient. So, but also if like for example the viscosity of the oils is lower, then the cells will grow in size, I would say.
Okay. And is there some not parameter but some number or something, some coefficient that will stay the same by changing the Rayleigh number? Just for one specific Rayleigh number, is there something that we can observe and it will be the same for all the experiments?
Well, I can't really understand your question. I'm sorry.
Yeah. Okay. I think that's okay. So now I would like to talk about the boundaries, because you said that you used two infinite free slit planes
Yes.
as your critical number. I found it quite interesting that you found that you would be able to clarify it experimentally. So there was no friction from the sides or from the bottom of your container.
Yes, that was the assumption that at the size there is no friction.
And for example, I would say that on the images we can say that the cells are somehow under some deformation. So
Yes.
could you elaborate on that?
Well, I think that the cells are deformed at the boundaries or at the balls because well, for some dishes, actually for a circular dish, the bottom of the container looks something like this. So this is a straight part where the cells can fully develop. However, here the fluid depth decreases quickly, and so the Rayleigh number is not critical. And so in this zone, well, it's not a stable condition. And also, so the cells cannot fully form at the balls because, well, as I mentioned, there is that extra condition of the force there, because as the fluid rises just next to, not next to the wall, but a little bit next. Yeah.
Okay.
You understand?
And,
So there is like this force because the fluid packets push away from the.
And did you somehow justify that there is no friction, or did you have some other experiment with something that would be more?
I think that
more
this measurement, that the critical number Rayleigh number is around 1700 is a justification for that, because if there were some friction, this wouldn't be the critical Rayleigh number according to your.
Yeah. Okay. I can agree with that. Okay. So I would like to. You said that the indicator is not important for the experiment, right? Or the phenomenon?
No, not the indicator, right? But you asked the temperature.
Or no, I was asking about the suspension. So I think
so
it's important to have the indicator in the oil.
Well, without the indicator, the convection will still develop. However, the indicator is allows us to
Yeah. So we would, of course, yeah. So we would need to use some other measurement techniques too, for example.
Sorry, can you repeat your question?
Yeah. So the convection would still happen, but we couldn't see it.
We couldn't see it. Exactly.
Okay.
Yeah.
And okay. And also when you are changing the different oils,
Yes.
were all the parameters the same, or rephrase it, you changed only the kinematic viscosity?
Yeah. Well,
Or was
according to the sheets I have received from the producer, there are like minor changes of the other parameters. But since the Rayleigh number is a critical parameter in the system, and it includes all of the relevant fluid properties, so I believe that it is.
Okay, I understand. And could you somehow elaborate on the figure that you had on the slide 16? I didn't have time to somehow.
16.
Yeah,
It's
because you said that this is kind of linear.
Yes.
And yes. So what was the main source of the error here?
So here, the main source of the error is like from the PIV analysis, from these averages. So I look at this graph. I take the maximal velocity, maximal vertical velocity component for a given temperature difference or for a given Rayleigh number, and then those are the points I have illustrated on that graph. And the error is like the standard deviation of the, so because I average all of these vertical velocity components, the standard deviation of that is my error.
Okay. And something about this method visualizer, I kind of don't understand how did you project it into 2D into 2D, because you shine through 3D
Yes,
correction.
so because of the PIV particles, they are fluorescent, and I have some like a ranch grade, optical grade here, which kind of opens up the laser.
Yeah.
So I get a laser plane, and I shine through that through my 3D convection, and
So
I
it was
only
just
see
2D plane.
from the side. I only see the particles which have some light shining on them because they are fluorescent. But I can't see the other particles which are out of the 2D plane, and that's how I can analyze the 2D section of the convection.
And on this figure, you have rectangle, or you have a square container.
Yeah.
So how does the shape of the cells differ from, for example, your cylinder one container?
Well, I would say that there are some minor differences at the edges, but since around the balls the cells can't really fully form, and they won't be shaped as this ideal hexagon from the top, it doesn't really matter in that sense.
Okay, so it would be just somehow
so
information, or
maybe we can look at this.
completely different.
Maybe we can look at this figure, because here you can see some non-ideal cell shapes from the side, and of course because of the non-linearity of the fluid dynamics in the whole problem, the shapes won't be optimal. But yes,
Okay.
that's because if you increase the Rayleigh number, the whole flow will be a little bit more like kind of chaotic, but not in
I
sense,
understand.
you know.
Yes. And one thing that I didn't see in the presentation, and
Yes.
it's something that I would like to discuss, is there some possibility to do some prediction about sizes of the cells or their shapes?
Well, for the we can talk first about the shape. So the ideal shape is hexagon, but you may ask why is that? It's because that's the ideal shape for the ideal heat transfer. So there are actually two shapes which can occur in between two infinite plates.
Yeah.
One is like if this is one plate, then this is the other, and we get these rolls.
Yeah.
This is one ideal shape. But if we superimpose these rolls onto each other, like we have one roll like this, then we have another roll like this, 60 degrees apart, and then also the third one, then these hexagons will form. And these are of course, very ideal. So during real measurements, you can't really get these hexagon shapes.
And if you wanted to somehow predict theoretical the size of them,
yes, well,
because something that I'm trying to talk about is how the Rayleigh number defines the cell. Because I think it would be possible, and I think it is possible to predict the size of the cells depending on the Rayleigh number.
So I believe that there are two phenomena which are present in for this. First is that of course the upward velocity of the fluid depends on the Rayleigh number. So when the fluid reaches the top, it will spread, and we might bring this spreading velocity from the Rayleigh number. But also, if we have small perturbations in our system just at the beginning, and if this is our system, and a cell is formed here, and it goes out like this, and then one forms here, so these cells will push against each other. And I would say that if the whole system is stable, then we might define the cell size by saying that here the fluid is more hot, here it's more cold, and we might work with these time
it is possible to do that.
Yes, it's quite hard, but
Thank you. Yeah, you can continue with your speech.
Yeah. So I would like to summarize the discussion that I had with the reporter. We discussed the oil relevancy and some different parameters that they changed. He said that they had different oils and changed local parameters, which I found very good. He also said that it's not important to have the indicator in the convection, which is something that is really important to say, that the convection does not depend on the indicator itself, but it's there only for our visualization. I think it's really nice that they use the PIV method and we could look on the convection not only from the top but also from the sides. We discussed the shapes and the size and shapes of each of the convective cells, and I think it's kind of lacking that there was no experimental technical model, because I think it's possible to do so. And thank you for your attention.
Thank you. Reviewer, you have 2 minutes.
So my first question will be to the reporter.
Yes.
Why do you think that the time of the displacement and the time of the thermal diffusivity need to have a certain ratio in order for the convection to also?
Right, so this actually comes down to the Navier-Stokes equations for this kind of convection, for Rayleigh-Bénard convection. We can solve them and also we introduce like a Busson-esque approximation. This is used for this. And if we really quantify the stability in the system, we get like a curve and it's minimal is when the Rayleigh number is.
Yes.
So that's why it's.
So what is the value of the Rayleigh number when the top boundary is free?
Sorry.
What is the value of critical Rayleigh number when the top boundary is free?
Well, it is 1700.
1700.
Yeah,
Okay,
exactly
and
that. Yeah,
what
exactly.
about for the opponent?
Yeah, for their assumption, it's exactly how they said.
Okay. So, did you measure the temperature on the top only in one point?
Yes. So we have like two sensors.
So the top sensors was fixated in particular points.
Yeah. So
surface.
but it was make sure that it's point like and it was calibrated beforehand and it really measured the temperature at the top and at the bottom.
Okay. So from which resources you take the thermal diffusivity and the viscosity values?
Sorry, can you please repeat?
From which resources you take the thermal diffusivity?
Oh yeah, so I have a spreadsheet from the producer of the oils. So
And what about the thermal diffusivity?
well, it was also included in the spreadsheet.
Okay. So my next question is going to be, how did you control the temperature difference on the top and the bottom?
So I actually, like I mentioned, this floated bath, which I have used for all my measurements. And so as I increase the temperature in the heater below the water will rise in temperature and it will cause a temperature.
Have you investigated the heating from the laser on the system?
No, but that I don't. It is irrelevant.
It is zero.
It is irrelevant.
And what the opponent thinks?
Yeah, I think I can agree with that method.
Okay. My next question going to be, have you accounted for the temperature gradient on the surface?
On this, what temperature gradient are you?
Have you accounted for temperature
Like at the
gradient on
top of the
surface?
stars?
Yes.
Well, no.
Okay. Do you have a theoretical prediction of the cell size?
Well, as we discussed with the opponent in the discussion, I have some. I don't have
Please short answer.
quantitative numbers, but I have some theory. Yes, qualitative theory.
What do you think the biggest problem of the report?
What?
What do you think is biggest problem of the report?
I think it's the lacking of the theoretical work.
Okay.
Okay.
Thank you. Preparation time. Yeah, please
Hello
start the
everyone, my
timer.
name is
Please stop.
Hello everyone, my name is Pak, and today I'm reviewing problem number 10, the Rayleigh-Bénard convection. So the problem states that we need to uniformly and gently hit the bottom of a container containing a suspension of powder and oil, and thereby select structures may form. Our goal is to explain and investigate this phenomenon. So first of all, let's start from the strengths of the report. First of all, the good experimental control, because the reporter measured the temperature both on the top and at the bottom, ensuring the right temperature difference. After that, the reporter also studied relevant parameters as a number of cells as well as temperature difference. Also, they analyzed a frequency as well as analyzing the velocity in the system. They also measured the critical Rayleigh number, both experimentally and theoretically. But as for numerous areas for improvement, there was poor explanation of the onset of the convection, because we actually want to have a more vivid explanation on why the temperature of the displacement and thermal diffusivity need to have a certain ratio. After that, the incorrect Rayleigh number used in the report, because in fact, when the top boundary is free, the Rayleigh number is equal to approximately 606. And there were no investigation of the edge factor. We would like to see more investigation of the edge factor, because the walls of the container also can transfer heat into the suspension. Also, poor explanation of why flows are visible in the report. However, after that in discussion, they clarified that it is due to different concentration of the powder in the suspension. However, our team actually believes that it is due to alignment of the powder particles in the suspension. After that, they didn't account for the top boundary, both in Rayleigh number and when measuring the temperature, because the temperature actually on the surface can be different. They also fully investigate the cell size. The reporter mentioned that that the cell size will be different. However, the reporter said that on the graph when he was investigating the number of cells, and it is not obvious why the cell size will be different and how what information we can derive from the number of cells about the cell size. So also he says that we see the direction of and no theoretical model for the characteristics of the cell as length or number, and we believe it is actually significant to fully investigate the problem, and also didn't account for the temperature gradient in the surface, which I already mentioned. And as for the opponent, about the strengths of the opposition, he clarifies a lot of aspects during the discussion. For example, different shapes and the oils variations used. As for the main problematic of the opposition doesn't really doubt the results of the reporter, but as I mentioned, with the free top boundary, the Rayleigh number will be drastically different, and the opponent also doesn't doubt the experimental control of the reporter. So as for the discussion, first of all, they discuss the deformation of the cells. The reporter they also discuss different variation of different types of oils, and they actually agreed with the opponent that it is significant and it was not depicted during the report. They also After that, they also discussed the cell size, and the reporter answered that the cell size is proportional to temperature difference. However, we disagree with this because in fact, when the temperature difference increased, the buying force increases too, and the number of flows and cells increases too, and the cell size will be decreasing.
Thank you.
Thank you for your attention.
You have 2 minutes.
Yes. So, thank you very much for the opposition and for the review. I'd like to clarify some things which were brought up in both of the presentation. So first, the reviewer asked about the temperature measurement at the top and whether I have taken into consideration the temperature gradient at the top of the cell. But I think that my measurement is valid because the sensors kind of measure an average top velocity, and yeah, so I think that I strongly believe that my methods are valid. About the critical range number, I disagree with the reviewer, and I still think that as I showed you, my measurements prove that the critical range number for these configurations I have used are 1708. Also, about the reviewer said that I stated during the discussion that the cell size is proportional to the temperature difference. I didn't say that. I said that it mainly depends on the temperature difference. However, it is quite difficult to set up like a dependence or like theoretically describe that, and that is because of the nature of the problem. So when I presented my theory to you, I have shown this ratio of timescales, and that is because well, of course we can describe theoretically the very ideal cells, but in reality that theoretical description is not enough, and you can't really describe the perfect cell sizes and shapes. Only you can describe trends, and I have kind of observed these trends, for example, for the upward velocity in terms of the temperature difference, and also the frequency, the oscillations of the cells all in all. So thank you very much for your attention.
Thank you. Yes. Let's have some questions. Who wants to go first? Please.
Yeah. Good report. In slide 4, I believe you calculated the Rayleigh number, which is quite important for the experiment.
Yes.
And I think, maybe it's a different one, but we know where we're talking about it. Yeah. And there's also the dynamic viscosity. And in my opinion, it's depending on the temperature. How did you control that, or did you make it
in my spreadsheets from the producer of the oil, they gave me a formula for the dependency, and I have used like the average temperature in my system. So basically, the average of the bottom and top temperatures, and I have calculated the dynamic viscosity for each Rayleigh number.
You made an average due to the temperature gradient.
Yes, yeah, basically, yes.
Questions?
Okay.
Please.
So you use the producer values. When I add the powder, any of these constants are changing?
I think that, well, the changes are irrelevant, I would say.
The reviewer, do you agree with him?
Could you repeat your question, please?
When I add the powder, the constants still the same?
Oh, I believe that viscosity increases.
Yes, please.
Maybe I can ask the opponent, or correct me if I'm wrong, but I think you mentioned that cell size can be predicted from the Rayleigh number.
Yeah.
Can you elaborate how?
Yeah, because the Rayleigh correction is well-studied phenomenon, and that's something that how he was talking about the Rayleigh number and the critical Rayleigh number. One can predict how the Rayleigh number can depend on some of the perturbations, as he was talking about, some wavelength or wave number, we could say, and the wave number is dependent on the size of the cells and the height of the oil in the container. So one can calculate for specific Rayleigh number, he can calculate the ratio of the size of the cells divided by the height of the cells.
Yes, please.
Maybe a question to the reviewer. You criticized that the reporter didn't calculate or measure the size of the cells. In average, I think you can calculate by area of the container and the number of cells. Yeah. What would you expect investigating the cell size?
Well, I would expect to firstly investigate the surface area of each cell, as well as maybe they take some length parameter in order to investigate the Rayleigh theory dependence that shows that dependence of the length of the cell on the height of the layer.
Maybe also to nobody else.
Not the same
Sorry.
questions to everyone.
I just moved that. Well, you can continue.
Can you go to slide 21?
Yes.
You have linear.
No, sorry. This one? 21.
It was the R square 0.788. Yes.
Oh, yeah.
Do you think that is a good linear fit,
Well-
and why? What is the physical explanation to not be a good linear fit?
Okay, so yes, I know that that is not the best fit, but I kind of expect a linear trend, because as we increase the temperature in our system, as I mentioned, there is more potential, and the slow movement of the cells. Well, the frequency of that I believe it should be around linear, maybe not perfectly linear, but yeah.
Yeah.
For the reporter, there's a clarifying question on slide 15. So
Yes.
there was an image, yes. So the image on the top is somehow discretized. So
Yes,
did you somehow decide on the discretization yourself?
Yeah, so I have implemented a MATLAB program which used my PIV videos, and it calculated the velocities because it looked at two consecutive
Okay, but on the
frames.
sizes of squares, did you decide on this, or how?
No, the program just gave it to me, but it
Okay.
looked at the PIV particles, and from that it gave me like an ideal discretization.
Thank you, and the time is up. Let's move on to grading. Yeah, yeah. So yeah, let's move on to grading. First, let's grade the reporter. So it is 6, 6, 6, 7, and 8. The opponent 6, 6, 6, 7, and 7. And the reviewer 6, 7, 7, 6, and 6. Just 1 minute. Thank you very much. So, for the lower end, you have 3 6s. Maybe one of you can comment and I will add.
Okay, yeah, I can comment. I really like the experimental setup, that was good. Also, my first question was that the fact that viscosity is temperature dependent, but you answered it in a logical way. Maybe the reason why maybe I ended on the lower spectrum can be that there was some qualitative comparison between theory and experiment, and I know this is a difficult task to do a quantitative one, but maybe if I have seen just like a try of quantitative agreement, then maybe I grade it a bit higher. But other than that, it was okay.
Yeah. Thank you. On the higher end, we have Otmar.
Yeah, I landed up at 8. I was between 7 and 8, and I rounded up 38. One thing was your really relaxed presentation style. It was easy to follow. You keep calm due to all questions, and you get good answers to our questions too. And of course, there could be a lack of experimental data. But in my opinion, your approach was to control the Rayleigh number. What's really important to that experiment. Maybe he could give us some references and citations where this problem is well investigated, and then therefore you need to take more and more experiment because there are a lot of data in the literature, and therefore I respected that and didn't penalize the presentation of more data.
Yeah, thank you. Yeah, I'll just briefly add something. Yeah, your presentation skills are wonderful, and the conduct of discussion is just the problem. Yeah, I absolutely agree with Marusz that it's very hard to write a theory here, and but like to read the score sheets and everything, I cannot give you a higher grade if there is like not at least like some approximate try to do so or something like that. So like I'm not asking of an exact theory that will match this point to point, but like you understand. So yeah, thank you. And for the opposition, we have 3 6s and Luis.
To the opposition, to the reviewer, sorry.
Opposition.
Opposition. Okay. I think you'll have good questions, but I think it was a really average discussion and the points you bring. So I gave you one. I like your discussion with the reporter. I gave 2, and I think it was this. I don't have any big things to say to you.
Thank you. And on the higher end we have, yeah, Justin.
Yeah.
Okay.
So yeah, as he rightly pointed, I like the way you have asked the questions. So I gave you around about 1.4, and during a discussion, I like the way you approach to the problem and how people have started doing the discussion. So I like the discussion pattern, and so I gave 2.6, which summed up to 7, 1.4, 2.6,
Okay. Thank you. And finally, it was a review. Yeah, I will shortly use the justification of the lower grade. Yeah, I just basically try to stay consistent. I didn't go higher for the opponent as well, and basically like opponent brought in some main stuff, and you brought in some stuff, but like not in too much quality, but like enough to like go one grade above the average review. So like, it was good, but like not like very very special or something like that. But yeah, it was good review in general. So yeah, I just give you it's a 1.5 in the clarifying results. This is which part I liked the most. The review report was okay also. What I didn't like and where I didn't go high was like review of opposition and discussion analysis where I just don't need but. And now the higher part the grades do not differ much, but Luis or Maroš, whoever prefers to do both talk, so.
Yeah, I can. Okay. I think take questions, you should. But in your presentation, you state 2 minutes and 37 seconds in the reporter, and I think you made good points about the reporter. Then you state 1 minute in the opposition, and it was kind of good, average. But when you go to discussion, you don't have a lot of time to discuss, and I really like to hear your opinion, because I really like your ideas of this problem. So it was for me a good reviewer, but it could be a little better in time.
Yeah, thank you everyone. If you do not have any specific questions, we can call a break up to let's say 5:55, so 8 minutes.